Welcome, everyone. I'm Dag Spicer, Senior Curator of the Computer History Museum. Today, we have with us one of the true giants in the history of computing, Dr. Stephen Wolfram, who will speak to us today about the origins and development of Mathematica and the Wolfram Alpha computational knowledge engine. Wolfram's career began early. He published his first scientific paper at age 15, and he received his PhD in astrophysics, I think. Theoretical physics from Caltech at age 20. So he's a bit of an underachiever, as you can see. But seriously, Wolfram has spent the last 30 years developing tools to help scientists and engineers and mathematicians deal with some of the drudgery that they deal with in their daily work. Over those years, he has extended Mathematica to include modules and procedures for addressing problems in a gigantic range of fields, from optics to neural networks, machine learning, statistics, electrical engineering, the list goes on. So Mathematica and the Alpha programming language, I think, are some of the most important pieces of software created in the last 30 years. And today we're going to have a wonderful chance to hear about that history. So please join me, everyone, in welcoming to the Computer History Museum, Dr. Stephen Wolfram.
Thanks very much. Okay. Well, so I normally spend my time trying to build the future, but I find history really interesting and informative, and I study it quite a lot. Some of you may have seen historical blog posts that I've written and so on. Usually I'm talking about other people's history. But the Computer History Museum asked me today to talk about my own history and the history of technology that I built. So for the first time ever, I think, I'm going to do that here. So this happens to be a really exciting time for me because a bunch of things that I've been working on for more than 30 years now are finally coming to fruition, finally coming together. Mostly that's why I've been in the Bay Area this week, for example, talking to lots of very different groups about those things. So the focus of what we're doing is a thing we call Wolfram Language, which is really a new kind of language, a knowledge-based language, in which sort of as much as knowledge as possible about computation and about the world is built into the language, and in which the language kind of automates as much as possible so one can kind of go as directly as possible from computational thinking to actual implementation. Well, I'm mostly going to talk about history here today, but I thought I should show you a tiny bit of what this language that I've been building for the last 30 or 40 years is about. So you kind of know where the decades of history that I'm going to talk about are actually taking us. So maybe I should start off by just showing you a very quick kind of live demo of Wolfram Language. And let's start off with the very basics. OK, 2 + 2 is 4, all good. Let's try something a bit more complicated. OK, we do a computation there. That's all good. We can, let's say we want to, I'm just going to type live here. I'm just going to say, let me make a plot here and make it something that I can manipulate. OK, there we go. Now I can do this and compute with it. OK, for example, let's say I want to deal with a language tries to deal with all sorts of different kinds of things. So for example, there's a graph. That might be my Facebook friend network, pretty good approximation to it, I think. I could say, make a plot of the kind of communities in that friend network. There's the result. I could go ahead and deal with other kinds of computation too. Let's say I do something like find the current image. So let me stand here. Let's do it again. OK, there we go. Pretty bad image. Now I can go and take myself and, let's say, edge detect that image. I get the result. Or I could say, let's dynamically edge detect the current image that I've got here. And I can do that and wave my arms around, and things will happen. OK? So a lot of stuff. Thanks. So so the idea of the language is lots of kinds of computational capability built in, also lots of things about the real world built in. So Mountain View is a city, okay, it knows what that is. I could say, what's the population of Mountain View, and it'll be able to tell me the answer. I could say, make some, let's say, I don't know whether it knows where we are here, but let's say we make some map where we're making a map of where we are. Let's say here, and then let's say I'm just showing you kind of what this language looks like. I'm going to make kind of a powers of 10 map around where we are right now, and let's see. Okay, so this should make, there we go. So now that's a map of here, mile, 10 miles, but probably 1,000 miles, 10,000 miles. So this is just using knowledge about the world. So we can do all kinds of things like this. We have a very wide range of different kinds of knowledge built into the system. Sort of one of the big things is being able to implement this in the cloud. Everything that you just saw me do, you can also get to by just going to our open cloud and playing with things. You can deploy this stuff in the cloud, use it for APIs, build all kinds of software technology with it. It's an exciting thing. But that's not what I'm going to talk about here today. I'm going to want to talk about sort of how all of this came to be and how Mathematica and Wolfram Alpha and other things kind of emerged along the way. And inevitably, a lot of what I'm going to talk about here today is really my story, basically the story of how I've spent most of my life so far building a big stack of technology and science. And kind of when I look back, some of what's happened sort of seems inevitable and inexorable, and some of it I did not see coming. So, okay, I'll start at the beginning. So I was born in London, England, 1959. So yes, by at least some standards, I'm outrageously old now. But my father ran a small company doing international trading of textiles for nearly 60 years, actually, and also wrote a few kind of serious fiction novels and things. My mother was a philosophy professor at Oxford University. I actually happened to notice that her textbook on philosophical logic is on the shelf in the Stanford bookstore last time I visited there, so that was nice to see. When I was 5 or 6 years old, I remember being bored at some adult party and ending up talking to some probably very distinguished Oxford philosopher who I heard, after he sort of walked away after talking to me, he said, "One day that child will be a philosopher, but it may take a while." Well, they were actually right. It's funny how these things work out. All right, let's see. Let's start off. That's probably me back in the day. So I went to. I'm giving you. I told you this is partly a story of me, but you'll find out how this all relates to technology and things I've done. So I went to elementary school in Oxford, to a place called the Dragon School, which happens to be probably the most famous elementary school. It's amazing that there is such a thing in England. Wikipedia seems to think these days that the most famous people from my class in elementary school that year are myself and an actor called Hugh Laurie, so who I knew quite well back in the day. So here's one of my school reports. I found this recently, actually, and from when I was 7. Okay. And this is England, so those are class ranks listed there. So yes, I did well in poetry and geography, but not particularly well in math. Yes, in England they had weird things like they taught Bible study and so on because that was the legacy of Henry VIII or whatever. But and then the end of this it says as the sort of summary, he is full of spirit and determination. He should go far. So that's okay. Well, that was in 1967, and I was, learning Latin and things like that. But what I really liked was the future, and the big sort of future-oriented thing happening back in those times was the space program. And I was really interested in all that, and I sort of started collecting all the information that I could about basically sort of every spacecraft that launched, and kind of collecting that together in little books and so on, and summarizing it. And I discovered that one can, even from England, one could, write off to NASA and get all this free, great stuff mailed to one. So back then, it was supposed to be the case that, there'd be a Mars colony any day. I think this was my little design for a Mars colony for the year 2000. And I started doing designs for that kind of thing, and designs for things about spacecraft and God knows what else. And that got me interested in, propulsion systems and ion drives and all kinds of things that were the future then and are still the future today. But by the time I was 11 or so, what I was really interested in was physics. I discovered, sort of having nothing to do with school and so on, that if one just reads books, one can learn stuff pretty quickly. And I would kind of pick up areas of physics and try to organize knowledge about them. Actually, when I was just turning 12 or so, I spent the summer kind of putting together all the facts I could accumulate about physics, and making these things. I suppose one could call these visualizations in today's world. Actually, this whole thing, if you can look at the stuff I did when I was 12, because it's on the web now. But I found this a few years ago again, and I was actually right around the time Wolfram Alpha came out, and I was like, my gosh, I've been sort of doing the same thing all my life in some sense. And then, of course, I started looking at the numbers from these things that I did when I was 12 years old, and typing them into Wolfram Alpha and seeing if I got the same answer. And yes, sure enough, in most cases I did. Well, so then, when I was 12 years old, following sort of the British tradition of these things, I went to a so-called public school. It's actually a private school. I went to probably the most famous such school. It's called Eton, that was founded about 50 years before Columbus came to America and so on. I actually, ever so impressively, I actually got the top scholarship among new kids who were going there in 1972, a long time ago. And yes, let's see, there's probably and back in those days, I think it's still the case, everybody there, wore tailcoats all the time, and the king's scholars, like me, also wore gowns, which I can say provided excellent rain protection and so on, if nothing else. I think this was a typical British picture, a very Harry Potter-like picture. I think I avoided these pictures all but one time. Actually, it's interesting what all these kids, these were scholarship kids, what all of them ended up doing. It's an interesting set of stories. But back in those sort of Latin and Greek and tailcoat kind of days, I had rather a double life doing, I did pretty well actually in those kinds of, composed Latin poetry and those kinds of wonderful pursuits. But my real passion was doing physics. And I guess for example, the summer when I was turning 13, I put together a whole big book of summarizing particle physics and so on. Again, you can find it on the web. I thought I should put, it sort of makes it clear this was written by a 12-year-old kid, but otherwise we're going to find lots of chunks of particle physics stuff quoted from here, which it's not bad, actually. It's not bad. But I kind of made the important meta-discovery at that time that even if one was a kid, one could discover stuff. And I started just trying to sort of answer questions about physics, either by finding answers in books or by figuring them out myself. And so by the time I was 15 or so, I started publishing papers about physics. And when you send a paper into a journal, nobody asks you how old you are. So it goes from there. But so something else important for me had happened when I was 12 years old and first at Eton, which was that I got to know my first computer. I don't think you have one of this particular species at this museum. Here's this is not the actual one of these that I used, but it's similar. It's an Elliott Marconi 903C. And it had come to Eton through a teacher of mine named Norman Routledge, who had been a friend of Alan Turing's. It had 8 kilowords of 18-bit ferrite memory, and it was usually programmed with paper or mylar tape. You can see there's the optical tape reader in the middle at the top there. And most often it was programmed in a little 16-instruction assembler called SIR. And it seemed like often using this computer, one of the most important skills was, after the tape would fly through the optical tape reader and wind up in a big wooden bin. And one of the big skills was being able to wind that tape back up again so that you could use it again and not tear it if it was paper tape. This is that's a summary of the instruction set of this computer together with its instruction times, 20 microseconds and so on. Not too shabby for the time. Anyway, I wanted to program this computer to do physics. And when I was 12 years old, I got a copy of this book. It's a standard kind of college physics textbook. And what's on the cover of this book is supposed to be a simulation of gas molecules showing sort of a trend towards increasing randomness and entropy. And as it happens, years later, I discovered that this picture on this book cover was actually kind of a fake. But back when I was 12 years old, I really wanted to reproduce this picture with a computer. Well, it wasn't so easy to do that because, the positions of the molecules, these are supposed to be real numbers. The computer didn't have real numbers. I had to have an algorithm for collisions between these things, and so on. And so to make all this stuff fit in a little Elliott 903, I ended up simplifying the model a lot and wound up with what's actually a two-dimensional cellular automaton. Well, a decade after that, I made some big discoveries with cellular automata, but back then I was kind of unlucky with my cellular automaton rule because it ended up not doing anything terribly interesting and I didn't discover anything very interesting, but I was really close to discovering some really interesting things back then. And in the end, with the Elliott 903, probably my biggest achievement was to write a paper tape loader. And I think this was made with my paper tape loader. The big problem in those days was, particularly with the mylar tape that one used for sort of more serious programs, is that it would get static electrically charged and it would pick up little confetti holes from paper tape that had been punched. And so the bits would get read wrong. And so for my loader, I came up with this bright idea of having what I later found out were called error-correcting codes. And I set it up so that when when the checks failed, if it couldn't correct itself, it would just stop in the reader, and you would physically pull back the tape a few feet in the reader, and then it would figure out how to line itself up again and read forward after you'd shaken out the little confetti hole that might have been there that caused the error to occur. Okay, so that was my big achievement back in the early days of my efforts in computers. But by the time I was, and the big issue was how you make the code loop be fast enough that it didn't slow the optical reader as it was reading through the tape. But so when I was, by the time I was 16, I had published some physics papers and started to kind of be known in physics circles. And I left school and went to work at a British government lab called the Rutherford Lab that did particle physics research. There's a typical paper I wrote. Well, you might remember from my age 7 school report, and there's a good theory that people never change, that I didn't do very well in math. So things got a bit better when I started to use a slide rule, and then in 1972 a calculator, of which I was a very early adopter. But I never really liked doing at least sort of school-style math, or math calculations in general. And in particle physics, there's a lot of math to be done. And so my dislike of it was kind of a problem. Well, at the Rutherford Lab, two things happened. First, there was a lovely HP desktop computer with a plotter, which I could use to do very nice interactive computation. And second, a mainframe for crunchier things that I typically programmed in Fortran. But so after time at the Rutherford Lab, I went to college in Oxford. Within a short time, actually, I decided this was sort of a mistake, but at least in those days, one didn't actually have to go to lectures or classes or anything, so I was not until sort of then you had to just do exams at the end of the year or something. You didn't actually have to show up to classes. So I was able to just spend my time kind of hiding out and doing physics research. And mostly I spent my time in a nice air-conditioned underground room in the nuclear physics lab that had terminals connected to a mainframe and also connected to the ARPANET. And that was when, in 1976, I first started using computers to do math, to do symbolic math and algebra and things like this. And Feynman diagrams in particle physics involve lots and lots of algebra. And there's sort of a long history to this. I mean, back in 1962, I think there were 3 physicists who'd met at CERN and sort of decided that, yes, it was a good idea to try and use computers to do calculations like Feynman diagrams algebraically. And they all had different approaches. One of them wrote a system called Ashmedai in Fortran. One of them, influenced by John McCarthy at Stanford, wrote a system called Reduce in Lisp. And one of them wrote a system called Schoonskip or Schoonskip or something, pronounced in Dutch, in CDC 6000 series assembly language. And the mnemonics for that system were, just to make it more user-friendly, were in Dutch. Curiously, of these 3 physicists, years later, one of them won a Nobel Prize for physics. And it turned out it was Tine Veltman, who's the person who wrote Schoonskip in assembly language with mnemonics in Dutch. Let's see, I probably have, oh yeah, there we go. There are some manuals of those systems. And there was some other systems that also existed for doing algebraic computation. And back in 1976, very few people, other than the creators of these systems, actually used them. But I started using them all the time. My favorite system was actually a quite different system written in Lisp at MIT since the mid-1960s. It was a system called Maxima that it ran on the Project Mac PDP-10 computer. And what was really important to me as a kind of 17-year-old kid in England was that I could get to it on the ARPANET. It was host number 236. And so you just go to an ARPANET terminal, you type @236, and there you were in an interactive operating system. When I first went there, somebody had taken the login SW, so I became Swolf, which I was for many years afterwards, and started to use Maxima. Well, I spent the summer of 1977 at Argonne National Lab, where they actually trusted physicists to be right in the room with the mainframe. Which was very, very helpful in both understanding and getting intuition about how computing really worked. Then in 1978, I went to Caltech as a graduate student. By that point, I think I was the world's largest user of computer algebra. And it was really neat because I could just compute all this stuff very easily. I mean, I used to have fun putting incredibly complicated ornate formulas in my physics papers. And then I could kind of tell when people were reading these things, because I get letters that said, you know, how do you get from line such and such in this paper to line such and such? Because, you know, how do you get all those weird, you know, 339 pi squared minus 33344 that's sitting right there. And I got kind of a reputation for being a great calculator, which was, of course, 100% undeserved, because it wasn't, you know, it wasn't me at all. It was just the computer. Actually, to be fair, there was a part that was me, because you see, by being able to compute so many different examples, I'd gotten kind of a new kind of intuition about things. So I was no good at computing like integrals and things myself, but I could go back and forth with the computer, kind of knowing from intuition what to try, and then doing experiments to kind of see what worked. So I was writing a whole lot of code for Maxima and building this whole tower of things. Let's see what I've got here. Well, that's probably a piece of Maxima code. That's probably a diagram of some structure of some routines that I was building. Notice there's a line in there that says Maxima reload. That's sort of a bad sign. Sometime in 1979, I sort of hit the edge of that technology stack and realized that something new was needed. And well, in November 1979, just after I turned 20, I put together some papers, called it a PhD thesis, and got my PhD. And a couple of days later, actually, I was visiting CERN in Geneva and sort of thinking about my future, and I thought in what I thought was basically going to be physics. And one thing I was sure was that what I would need was something beyond maxima and so on that would let me kind of compute things. And that was when I decided that I had to build a system like that for myself. And well, right then I started kind of handwriting the specifications for such a system. Originally, it was going to be called Algae, the algebraic manipulator. But I kind of quickly realized that I actually had to make it do much more than just algebraic manipulation. And I knew most of the kind of general purpose sort of algol-like languages, and as well as languages like Lisp and APL and so on at the time. But somehow they didn't seem to capture sort of the things that I wanted my system to do. And so I guess I did what I'd sort of learned to do in physics, which was I tried to sort of drill down to find kind of the atoms, the primitives of what was going on in all these computations that I wanted to do. And I knew a certain amount about mathematical logic and the history of attempts to formulate things using logic and so on, even if my mother's textbook about philosophical logic didn't exist yet. But you know, the whole history of this effort at formalization I was quite aware of through, you know, Aristotle and Leibniz and Frege and Peano and Hilbert, Whitehead, Russell, and so on. It's all a very interesting history. But anyway, that's a different talk. But back in 1979, I was sort of thinking about this kind of thing, and that led me to the design that I came up with, that was sort of based on the idea of symbolic expressions and doing transformations on symbolic expressions. So I named what I wanted to build SMP, the symbolic manipulation program, and I started recruiting people from around Caltech and so on to help me build it. Richard Feynman actually was somebody I knew pretty well at that time, and he came to a bunch of meetings that I had to sort of discuss the design of SMP, offering various ideas, which I have to admit I often considered quite hacky, but typically about sort of shortcuts and interacting with the system and so on. Meanwhile, the physics department at the theoretical physics group at Caltech had just gotten a VAX 11780, and after considerable wrangling, it was made to run Unix. And there was a young physics graduate student named Rob Pike there, who more recently is the creator of Go, for example, who persuaded me that I should write the code for SMP in the language of the future, C. So I was myself actually pretty good at writing C, and for a while I think I was averaging about 1,000 lines of code a day and so on. And with the help of a somewhat colorful collection of characters, by June 1981, the first version of SMP existed with a big book of documentation and things that I'd written. Look at this, I actually have it, it exists. So you might ask, can we actually see SMP running? Well, back when we were working on SMP, I had the bright idea that we should protect the source code of SMP by encrypting it. And you guessed it, over a span of 3 decades, nobody remembers the password. And until a little while ago, that was the situation. But, and in fact, even in another bright idea, I'd used a modified version of the Unix script program to do the encryption, thinking that that would be sort of more secure than the generic Unix script program. Well, actually, as part of the 25th anniversary of Mathematica a couple of years ago, we did sort of a crowdsourced project, and we succeeded in breaking the encryption. So now we have the source code again. Unfortunately, it was not easy to compile the source code, but actually a 15-year-old volunteer eventually got this working, and it's funny how that works out. I think, and it's working inside a VAX emulator, and there is a chance, let me see, can I do this? There is a chance that for the first time in public in 30 years, I may be able to show you a running version of SMP. So let me just see whether I can do this. Run SMP. Let's see what happens here. OK, that's booting up the VAX emulator. Come on, wake up, wake up, wake up. Go for it. See what happens. Ta-da, login. OK, let's log in. Aha, there we are. OK, that is an SMP prompt. Let's see what it does. OK, it still knows what 2 + 2 is. Terrific. After all these years, this is from August 4th, 1986, this version. So, okay, 10 factorial. I don't know what happens if we go higher than that. Okay, it's starting to see if it can do. Let's see if it can. I have no idea. See if it can do. Ah, okay, it lives. Let's try doing some algebra. You know, one of the mistakes that I made in SMP was these short command names. I remember talking to Dennis Ritchie and Ken Thompson about this at some point in the early 80s, and they were saying, like, SMP was really cool, had nice short command names. That turned out to be a mistake. But in those days, the typical person didn't know how to type very well, so it actually was a good thing. Okay, so it can still factor polynomials. Let's see whether it can do an integral here. Okay. It's not the best form of that integral I would like to see, but it's okay, not so bad for a thing that old. And let's see, let's try and do something like this. Yeah, okay, that will make arrays of things. Okay, let's really live dangerously here. Let's say we try to do something like this. What is it going to do? I don't try this, but let's try it. Aha! Look at that, ASCII. And I think it even made some 3D ASCII renditions of things. But, okay. So, and then it had some really wacky stuff. Like this was, if I remember correctly, this is Rex, the random expression generator. So you type in, let's see what happens. I bet, okay, there we go. So there's a size 1000 random expression generated, which might have been useful for testing. I'm not really sure. So anyway, SMP had a mixture of some good ideas and some very bad ideas. One example of a very bad idea, which I have to admit was actually suggested to me by Tini Veltman, the author of Schoonship, was representing rational numbers using floating point inside so that one could take advantage of kind of faster floating point units and then kind of trying to fix things up on the back end to see whether one was close enough to a rational number that it would be right. That was a really bad idea. There are plenty of other bad ideas, too, like having a garbage collector that had to sort of crawl back through the stack and realign pointers dynamically as it ran. There was plenty of interesting ideas. There was a thing that I called projections, which were essentially a unification of functions and lists. They were almost wonderful, but there were kind of confusions about what's now called currying. I used to call tiering. And there were sort of weird edge cases about vectors that were almost sort of symbolically indexed lists that were almost sequential vectors and so on. Well, all in all, SMP worked quite well, actually. And I certainly found it very useful. So the next problem was sort of what should I do with it? And I realized it needed a real team to work on it, and I sort of thought the best way to get that was somehow to make it commercial. Well, at the time, I was a 21-year-old kind of physics professor type who did not know anything about business. So I thought, okay, I'm at Caltech, let me go to the tech transfer office, which I saw in the phone book type thing at the university, and ask them what to do. And it turned out that they didn't know, and as they explained to me, it's because, well, professors mostly don't come to us. They just go off and start their own companies. So I said, well, okay, can I do that? And right then and there, the guy who was their lawyer at the technology transfer office sort of pulled out the faculty handbook and looked through it, and I think I might have got a copy. Let's see if this is it. Yeah, I think so. And pulled out a particular page of the thing and was very happy to discover that, well, yes, it says copyrightable materials are owned by their authors. Software is copyrightable. You don't have to talk to us. Thank you very much. My job is done here, so to speak. You can do whatever you want. And so off I went to try to start a company. It turned out not to be quite so simple because at some moment the university sort of decided that actually I really shouldn't do just what I wanted. And a couple of years ago, actually, I was visiting Caltech, and I ran into the now 95-year-old chap who had been the provost at the time when I was at Caltech. And he finally filled in some of the remaining details that I didn't know of what he referred to as the Wolfram affair. So actually, the details are more bizarre than one could possibly imagine, or I could possibly imagine. Suffice it to say that the story actually starts in 1929 when Arnold Beckman was a postdoc at Caltech and invented the pH meter and said he owned the rights to the pH meter, and he went off and started Beckman Instruments. Well, back in 1980, Arnold Beckman was sort of involved with Caltech as the chairman of the board of trustees and so on, and ended up being really upset when he realized that the gene sequencing technology that had been developed and invented at Caltech had kind of, as I believe it was said, walked off campus and turned into applied biosystems. So that kind of, I happened to be sort of the other IP thing that was happening on campus at the time, and there were all kinds of issues associated with that. But anyway, the company that I started weathered this particular storm, even though I ended up quitting Caltech, and Caltech ended up with a really weird software ownership policy that sort of affected their computer science recruiting efforts for a long time thereafter. But I didn't do a particularly great job starting what I called Computer Mathematics Corporation. I brought in a person to be CEO who happened to be twice my age, which ended up creating all sorts of problems. And rather quickly, things diverged from what I thought was sensible. There was, there's an SMP brochure. There's a less convincing ad for computer algebra that was subsequently run. Actually, one of my favorite moments of insanity, I might relate, was the idea of that we should get into the hardware business and build a workstation to run SMP on. At the time, no workstation had enough memory. The 68000 did not handle virtual memory. And so a scheme was concocted whereby there would be two 68000s running an instruction out of step. And when the first one saw a page fault, it would kind of tell the other one to stop and fetch the data. And I thought this was a completely nutty scheme. And I also happened to have visited Stanford and run into a graduate student named Andy Bechtolsheim there, who showed off a Stanford University network workstation that was at that time in a cardboard box. But it was clear where the future was going. But worse than all that, this was 1981, and there was the idea that AI, which was big then, in the form of expert systems, was hot. And so the company merged with another company that did expert systems to form what was called Inference Corporation. SMP was kind of the cash cow selling to corporate research labs for actually often $40,000 a copy and so on. But the venture capitalists who'd come into the thing were convinced that the future was expert systems, and that was where the company should go. And after not very long, I left. Meanwhile, I'd become a big expert on the intellectual policy properties of universities. And eventually, I went to work at the Institute for Advanced Study in Princeton, where the director of the place, when he was recruiting me, had very charmingly said that since they'd given away the computer after von Neumann had worked there and when von Neumann died, that it didn't really make sense for them to make any claims to intellectual property rights thereafter. So anyway, I was at the Institute for Advanced Study in Princeton, and I kind of dived into doing basic science, working a lot on cellular automata, discovering some things I thought were very interesting that sort of have ended up forming the basis for things in complexity theory and so on. Let's see, here's a picture of me with my Sun workstation and more hair, running with cellular automata running on the Sun workstation. I think that's a Sun 1. Here's another example. And yes, the mollusk shell, which I think I'm holding upside down there, really does look like the cellular automaton on the screen. Well, I did, in addition to doing basic science, I did a certain amount of consulting work, mostly about technology strategy, which was extremely educational, particularly in seeing lots of things not to do and so on. But anyway, I did, for example, quite a lot of work for a company called Thinking Machines Corporation. I think probably my most important contribution to that company was going to see a movie with its founder, Danny Hillis. We went to see the movie War Games. And as we were walking out of that movie, I said to Danny, you know, maybe your computer should have flashing lights too. So, well, I was mostly working on basic science, But quotes, sort of because it would be easy, I decided to do, one software project, for example, which was building a C interpreter. And I hired some young people, one of whom was a chap called Tsutomu Shimomura, who I had actually already by that time fished out of several hacking disasters. He went on to be famous for another hacking-related thing. But I made the horrible mistake, actually, in that project of saying, well, I've got all these slightly younger than me people who want to do all this exciting stuff. I'll just do the boring code myself. So I wrote a quite lovely text editor, but the rest of the project didn't quite make it, and the whole thing didn't happen. But that was kind of a side project of mine. So I had all kinds of interactions with the computer industry back when I was at the Institute in the early 1980s, as a result of having gotten to know people through SMP and so on. I could tell you all kinds of stories. I remember, here's one. I remember a chap called Nathan Myhrvold, who was then a graduate student at Princeton, came to see me one day to ask, with some of his friends, to say they developed this Windows system, and what should they do with it? And so I suggested maybe he should sell it to Microsoft, which he did, and later on Nathan became CTO of Microsoft. By about 1985, I'd done a bunch of basic science that I was pretty pleased with, and I was trying to use it to sort of start the field of what I called complex systems research. I ended up getting a little involved in an outfit called the Rio Grande Institute that later became the Santa Fe Institute, and sort of encouraging them to pursue this kind of research. But I wasn't convinced about their particular chances, so I resolved to start my own research institute. So I went around to a lot of different universities, in effect, to sort of get bids for starting this research institute. And the University of Illinois won, ironically, in part because they thought it would help their chances of getting funding from the Beckman Foundation, which in fact it did. So in August 1986, off I went to the University of Illinois in the cornfields of Champaign-Urbana, 100 miles south of Chicago, and started the Center for Complex Systems Research. So I think I did pretty well at recruiting faculty and setting things up for the new institute, and the university lived up to its end of the bargain too. But within a few weeks, I started to think that it was all a big mistake. I was spending all my time managing things and trying to raise money and not actually doing science, which was kind of my main point. So I kind of quickly came up with Plan B. Rather than getting other people to help with the science that I wanted to do, I would just set things up for myself so that I could just do the science myself as efficiently as possible. And this meant two things. First, I had to have the best possible tools, and second, I needed the sort of best possible environment for myself. So when I was doing basic science, I kept on sort of using different tools. There was some SMP, there was quite a lot of C, PostScript, graphics libraries, and so on. A lot of the time was spent kind of gluing together all of this stuff. And what I decided was that I should try to build sort of a single system that would just do all the stuff I wanted to do and that I could expect to keep growing forever. Well, meanwhile, personal computers were just getting to the point where it was plausible to run a system like this on them. And I knew about quite a lot about what to do and not to do from my experience with SMP. So I started designing and building what became Mathematica. So my scheme was always to write documentation to define what I wanted to build. And I wrote a lot of, I don't know what these are. These are some early people who know Mathematica. There's you can see some early places of working out various pieces of syntax and things here. So I wrote a bunch of core code for Mathematica myself. For example, the pattern matcher, a surprising amount of which code is actually still in the system all these years later, somewhat to my horror, I suppose. But people say it's good code, so whatever. So the design of Mathematica was in many respects sort of less radical, less extreme than SMP. SMP had really insisted on using the idea of transforming symbolic expressions for everything. But in Mathematica, I saw my goal as being sort of to design a language that would effectively capture all possible different paradigms for thinking about programming in a nice, seamless way. Well, at first, of course, Mathematica wasn't called Mathematica. And a strange piece of later fate, it was actually originally called Omega. Well, it went through other names. There was Polymath, Technique. Here's a list of some of the names we considered, including some of the... and it's actually kind of shocking to me how many of these names, even the impossible names at the bottom, like Mathosaurus and so on, have actually been used by products in the years since this list was made. Well, so I was working on the code and the design of Mathematica. Meanwhile, I was starting to investigate how to build a company around the system. My original model was to do something like what Adobe was doing at the time with PostScript, to sort of build core IP and then license that to hardware companies to bundle. And as it happened, the first person to really show interest in doing that was Steve Jobs, who was at that time in the middle of doing Next. Well, one of the consequences of interacting with Steve was that we talked a bunch about things like the name of the product. And with all that Latin that I had learned in school, I'd thought about the name Mathematica, but I thought that it was too long and ponderous. And Steve insisted that that's the name, and had this whole sort of theory about taking generic names for things and kind of romanticizing them and so on. And eventually he convinced me, and so Mathematica became the name of the system. It took about 18 months to build version 1 of Mathematica. I was still officially a professor of physics, math, and computer science at University of Illinois, but apart from that, I was sort of spending every waking hour sort of building software and making deals and things like that. We made a deal with Steve Jobs to bundle Mathematica on the Next computer. We also made a bunch of other deals with Sun through Andy Bechtolsheim and Bill Joy, with Silicon Graphics through Forrest Basket, with Ardent through Gordon Bell and Cleve Moeller, with the AIX RT part of IBM, and so on. And eventually we set a release date, June 23rd, 1988. And so as sort of documentation for the system, I wrote a book called Mathematica, a system for doing mathematics by computer. Yes, it really exists. It was going to be published by Addison Wesley Publishing Company, and it was sort of the longest lead time element of the product release. It ended up being very tight because the book was sort of full of fancy PostScript graphics and so on, which apparently at the time nobody could figure out how to actually render at high enough resolution. And so eventually I ended up having to sort of solve this problem and took a hard disk to a friend of mine in Canada who had a phototypesetting company, and he and I kind of spent a holiday weekend babysitting his phototypesetting machines, after which there was a big stack of film, and I flew to Boston and handed the film to the production person from Addison Wesley, and off the book went to be printed. Anyway, we decided to do the announcement of Mathematica in Silicon Valley, and specifically at the Tech Mart in Santa Clara, which I guess probably still exists. In those days, Mathematica couldn't run on MS-DOS because of the 640K memory limit. So the only consumer version was for the Mac. And the day before the announcement, there we were kind of stuffing boxes and delivering them to the Computerware software store in Palo Alto. And I think I have, yes, I do. I have. This is an actual original version 1 box with its, what does it have in it? What do we have in it? It's been packed too well here. Okay, there are the distribution disks. A bunch of distribution disks. And a bunch of foam that I think the idea of this box was, yes, the idea of the box was you fit the book in the box. And in the cases where the book wasn't there, you put foam in the box instead. But anyway, the announcement on June 23rd, 1988 was a nice affair. Steve Jobs came, for example, even though he was not really out in public at the time. Larry Tesler came from Apple, very courageously doing a demo himself, software. John Gage from Sun had the sense to get the various speakers that we had at the event to sign a copy of the book. that we had there. And we had Mathematica running on a Mac. I actually got it running again recently, and I had meant to get a video of it, but I didn't have a chance to do that here. But in any case, that was so that was how Mathematica was launched. The Mathematica book actually became a bestseller in bookstores, and from that, lots of people started understanding kind of how to use Mathematica. And it was really neat seeing how all these kind of science types who had never actually used computers themselves before. They'd always said, if I want to do a computation, I'll find a graduate student or a programmer or something to do it for me. They were actually starting to type with their own fingers and use computers themselves to do things, which made their work much more efficient. So it was fun kind of looking through the old registration cards and so on. I don't know what these particular ones are, but we have all of them. Lots of interesting and famous names, sometimes some nice juxtapositions. I remember one time I had just seen an article about Roger Penrose and his new book in Time magazine that had the headline, "Those Computers Are Dummies." And then literally I was then looking through our registration cards a few minutes later, and there was Roger's registration card for Mathematica. So that was kind of nice. So it's as part of the growth of Mathematica, we ended up interacting with pretty much all possible computer companies and collected all kinds of exotic machines. I mean, sometimes that came in handy, like when the Morris worm came through the internet. Our gateway machine was some weird Sony News workstation with a Japanese OS that the worm had not been built for. So that was a nice kind of added benefit. But there were all kinds of porting adventures. Actually, this is kind of a trip down memory lane. This is the price list for Mathematica 2.0 on machines like Convex and Data General and MIPS and so on. And there's the Sony News machine for $2,000. It's actually about the same as the price of Mathematica today. In any case, probably my favorite moment of porting was on the Cray 2. With great effort, we'd gotten Mathematica compiled and was running on the Cray 2, and there we were ready for the very first calculation. And someone typed 2 plus 2, and I kid you not, the answer that came out was 5. I think it was an issue with kind of integer versus floating point representations because the Cray was really optimized for floating point kinds of things. Well, so we were off and running with Mathematica. Got another boost when the next computer came out with Mathematica bundled on it. I think Steve Jobs made a good deal getting Mathematica bundled on the Next because an awful lot of people bought Nexts to run their free Mathematica, so to speak. Like, for example, the theory group at CERN did that. And the person who was running those computers at the time was a certain Tim Berners-Lee, who ended up using the computers that had been bought for Mathematica to do an extra little experiment with networking on the side, which turned into the web, in case people don't know that history. Well, a couple of years in, the company was growing nicely. We had maybe 150 employees. And I thought to myself, I built this technology because I wanted to have a way to do science. So isn't it time I actually started doing that? So also, to be fair, I was injecting new ideas into the company at probably too high a rate. And I was sort of worried the whole company might just sort of fly apart through idea density. But anyway, I decided I would take sort of a partial sabbatical and for maybe 6 months or a year, do basic science and write a book about it. So I moved from Illinois to the Oakland Hills, right near here, right before the big fire there, which fortunately narrowly missed our house. But I started being a remote CEO, using Mathematica all the time to do science. Well, the good news was that I started discovering lots and lots of science. It was kind of a turn a telescope to the sky for the first time moment, except that now it was sort of a computational telescope looking at the computational universe of possible programs. And it was really great. I just couldn't stop, and because there was just kept on being more and more things to discover. So all in all, I kept on doing that for 10 and a half years. I was really kind of a hermit, mostly living in Chicago in the end, and mostly interacting only virtually, although my oldest 3 children were born during that period, so there were other humans around. But I thought maybe there'd be sort of a coup at the company, but there wasn't, and the company continued to grow steadily, and we kept on doing new things. I mean, you know, there's our first website from early in the days of the web, and not long thereafter, we put our first computation that was done on the web, but still running today, actually. The server for this actually stayed up for many, many years at a time. Well, I actually took a break from my science back in 1996 to finish a big new version of Mathematica. Back in 1988, lots of people used Mathematica through a command line interface. In fact, it's still there today. You know, you can go to it, and I always used to use the 1989 to the power 1989 computation as a sort of test of the speed of computers. And yes, you can go to a Raspberry Pi. Raspberry Pis have a bundled version of the Wolfram language on them, and you can test it out, that computation from the command line, and that all still works today. Actually, the original version of the Raspberry Pi gives a pretty good simulation of what it was like to use the system on computers back in the day when Mathematica first came out in 1988. But okay, on the Mac and the Next, back in 1988, we'd invented these things we called notebooks that are documents that mix text and graphics and structure and computation, and that was the UI. The notebook interface was the UI for Mathematica. It was very modern, had a very clean kind of front-end kernel separation, where you could run kernels on remote computers, for example. And by 1996, it had sort of a complete symbolic XML-like representation of the internal structure of these notebooks and so on. Actually, perhaps I should say something in general about the software engineering of Mathematica. The core code was written in an extension of C. Actually, it's an object-oriented extension of C that we had to develop ourselves because back in 1988, C++ wasn't yet efficient enough for us to use it. Even from the beginning, some code was written in the Mathematica top-level language, that's now the Wolfram language. Over the years, the fraction of code that's written in the Wolfram language has gotten bigger and bigger. Well, back at the beginning, it was very challenging getting the front end to run on different machines, and we wound up with different code bases on Mac and Next, and eventually Microsoft Windows and X Windows. And then in 1996, one of the big achievements was merging all of those code bases together. So we had a beautiful, uniform code base for our user interface. And for 20 years, it was all gloriously merged. But now, again, because of the realities of modern times, we've got to have separate code bases again for desktop and browsers and on the web and mobile, and the history is repeating itself. But anyway, back in 1996, we had all kinds of ways to, we were doing all kinds of things. We had this great new version of Mathematica, version 3. We had all kinds of ways to get the word out. Let's see, do I have a picture of that? Maybe I don't. Oh, that's a shame. Oh, here, I have to go. You know, if you're interested in the history of this stuff, at the 25th anniversary of Mathematica, we created a website called Mathematica25.org, and I'm going to have to go there because I don't seem to have this picture anywhere else. We, as part of the kind of promotion for, okay, that was an early news article about, I still like those ice creams, actually, about Mathematica, and that was an IBM poster about Mathematica. We never really made any deal to speak of with Apple, but Apple did make a nice poster. Oops, let's see. I was going to find our promotional vehicle. Where is it? Come on, it's got to be here somewhere. that was the company back in the 5th anniversary of the company back in 1993. Well, 5th anniversary of Mathematica back in 1993. There we go. Here it is. That's the guy. So this was one of our 2 promotional vehicles we called Mathmobiles that drove around with the latest gear inside, one in the US, one in Europe. It was in Europe, the most dramatic moment was when one of these things got stuck in the gate to a walled city in Europe. But that had some creativity in getting it out again. But these were kind of moving billboards with all our nice graphics on them and so on. Well, there started to be Mathematicas all over the place, getting used for all kinds of things. Of course, there were wild things that happened sometimes. One story from 1997, there's a chap called Mike Foale, who's an astronaut who had a PC running Mathematica that was on the Mir space station with him. And well, there was an accident on Mir, and the PC that he was using got stuck in a part of the space station that was depressurized and couldn't be reached. Meanwhile, the space station was tumbling, and Mike really wanted to debug that by solving equations of motion for the space station in Mathematica. It's the calm way to handle these things. But anyway, he finally got a new hard disk with a version of Mathematica sent up on the next supply mission, and then installed it in a PC that he had there, which was a Russian PC. But there was a problem because our DRM system immediately said, that's a Russian PC. You can't run a US-licensed Mathematica there. And that led to probably our all-time most exotic customer service call. You know, the user is in a tumbling space station. Please give us a new password. And fortunately, we did, and Mike figured out how to make the space station stop tumbling. I think the Russian ground controllers, though, insisted on using one of their by-the-book solutions, not the better thing that he'd figured out. But anyway, the space station was stabilized. The Mathematica and Mike came back safely to Earth, and everybody lived happily ever after. Well, after a decade or so of kind of Mathematica development, me working on my big basic science project, in 2002, I finally finished my big science project and produced my book about that, which maybe I have a picture there. Yes. Strangely enough, in the world of learning about typesetting and books and so on, this book had another glitch. It was actually being printed over another holiday weekend in a direct-to-plate photo typesetting system, and we noticed that a bunch of its very high-resolution graphics had horrible glitches in them. And I eventually had to send email to John Warnock, who was helpful enough to eventually tell me that there was a bug in PostScript that had been there for 10 years or something that we'd found in printing this book. So I've had adventures in putting things on paper multiple times. But in any case, the thing that, so my big book came out during the sort of my science decade. The company had been steadily growing, and we built up a terrific team of people. And not least because of things that I'd learned doing my science, I thought we could do a lot more with our technology. And it was sort of refreshing, actually, to come back to focus on the technology again after having been sort of away for a decade doing science. And I rather quickly realized that the structure that we'd built could be applied to lots of new things that we hadn't thought of before. So math had been sort of the first big application of Mathematica, but the symbolic language that I built was much more general than that, and I knew that from the beginning. And it was sort of exciting seeing what we could do with it. I mean, you know, in 2006, we sort of understood how to represent user interfaces symbolically and be able to create them computationally, and that led, for example, to CDF, our computable document format that led to things like our demonstrations project. We started doing all sorts of experiments with our technology. Some went really well, some went a bit off track. I mean, for example, we thought, let's take our knowledge base of mathematical functions and make a sort of poster summarizing facts we know about mathematical functions. Well, first it was going to be a small poster, then it was going to be a poster that became 36 feet of poster, and eventually it turned into a website with 300,000 relations about mathematical functions on it, and now it's turned into some pieces of Wolfram language that have many more hundreds of thousands of relations about mathematical functions. Curiously, some of them produced by some people who joined our company many years ago, who I think I can call the last of the Russian integral table makers, who used to produce paper books of these kinds of things and have now been able to produce vastly more online, so to speak. Well, back in those days, it was the time of the cell phone ringtone craze. And I at some point had wanted a personal ringtone. So, this is one of these CEO of private company kinds of problems of CEO wants something and says, let's go build this thing. And so we decided we would make a way of coming up with, using cellular automata, to come up with an infinite variety of unique ringtones. And so we put this on the web, and it was actually a pretty interesting sort of AI creativity story. And music people actually liked it quite a bit. But after messing around with phone carriers and so on for about 6 months, we didn't sell a single ringtone. Actually, this site is still up, although it's a little bit embarrassing because right now I think it is not working with the current browser releases. That will be fixed soon. But what happened is this is running off a web version of Mathematica, and literally this site has been running without being rebooted for many, many years, and it's not clear anybody. We don't actually have anybody who quite knows exactly how it works. So that's been it'll be re-implemented in our new technology stack. But anyway, so for many years we'd been a sort of a one-product company making Mathematica. And we were starting to get the idea that we could not only add lots of things to Mathematica, but also invent all kinds of other stuff. Well, I mentioned that back when I was a kid, I was really interested in trying to do what one could now call make knowledge computable. Sort of take knowledge that has been accumulated in our civilization and build something that could kind of automatically compute answers to questions from that base of knowledge. And for a long time, I'd sort of assumed that to do that would require making some kind of sort of brain-like AI. So like back in 1980, I worked on neural networks and things and didn't get them to do anything very interesting. Actually, I worked on neural networks before I even worked on cellular automata. Every few years after that, I would sort of come back to it again and think again about this kind of computational knowledge problem. And then I did the science in my book, New Kind of Science, and I discovered this thing that I call the principle of computational equivalence, which says many things. But one of them is that there sort of can't be a bright line between intelligence and, in a sense, mere computation. And so that made me start to think that maybe I didn't need to sort of build a brain to solve the computable knowledge problem. Meanwhile, my youngest son, who was, I think, about 6 at the time, was starting to use Mathematica a bit. And he kept on asking me, why can't I just tell it what I want to do in plain English? And I started explaining to him how hard that was. But he kind of persisted and said, look, there just aren't that many different ways to say these things. And surely you can just write code that does this and such like. And that kind of got me thinking, particularly about using the science that I built to try and solve the natural language understanding problem. Well, meanwhile, I started a project to kind of curate lots of data of all kinds, and it was an interesting thing, going into a sort of big reference library and figuring out what it would take to make all of that data that we could see in all these books computable. I mean, actually, Alan Turing had done some estimates of things like that, which were quite daunting. Anyway, I started getting all these experts on all kinds of things, and on all kinds of topics that tech companies usually don't care about. And I started building technology and sort of a management system for making data computable. It was not at all clear that this was going to work. And even a lot of my own management team in my company were quite skeptical. I mean, it was another Wolfram tones was a common characterization of what we were doing. But the good news was that our main business was strong, and well, actually, even though I'd considered it in the early 1990s, I'd never taken our company public, and I didn't have any investors at all except for, I guess, myself. So I wasn't really answering to anyone, and so I could just do big projects, and for example, do the Wolfram Alpha project, and that's been something that has been a great feature of our company, which is now nearly 30 years old, being able to concentrate, being able to do things that have these very long time horizons. Well, despite all the concerns, the thing that became called Wolfram Alpha did actually work. And I have to say that when it was finally ready to demo, it was really nice that it took just one meeting for my management team to go from being deeply skeptical to being very enthusiastic and figuring out all kinds of ways that we could do things with this technology that we built. Well, one problem, of course, with Wolfram Alpha is that, like Mathematica and now the Wolfram Language, it's really an infinite project. But there came a point when we really couldn't do much more development of the system without seeing what would happen with real users asking real questions, using real examples of natural language. So we eventually picked May 15th, 2009 as the date to go live with what we'd built. But there was a problem. We had no idea how high the traffic would be when we first put this thing out in the world. Back then, we couldn't use things like Amazon or anything. To get the performance, we had to do fancy parallel computations right on sort of bare metal and so on. Actually, Michael Dell was kind enough to give us a good deal on getting lots of computers for our colos. But I was pretty concerned when I talked to some people who'd had services that they'd launched that had sort of crashed horribly on launch. So I decided that the way we would do our launch was kind of a hack. I decided that we'd launch what we did on live internet TV, so that if something horrible happened, at least people would know what was going on, and everybody would have some fun with it. So I contacted actually a chap called Justin Can, who was then doing a thing called Justin.tv, and whose first company I'd actually failed to invest in when I'd seen it at the very first Y Combinator, even though one of my oldest child had told me that's the company to invest in. It was the 11-year-old picking companies. But anyway, eventually the descendants of that company did very well. But we arranged to use that live sort of internet TV mechanism to do our launch on kind of do it live. So it was sort of fun building our kind of mission control type setup. We had some, those are just pictures. Let's see, there's a good one. Yeah, okay, we had, it made us build some nice dashboards, some of which we actually still use today. But the day of the launch, actually, I was concerned that this was going to be the most boring TV ever. That basically, at the appointed hour, I just click a mouse and we'd be live, and that was the end of it. Of course, it wasn't quite as simple as that. There's actually, you can find the video of the thing online somewhere. I haven't watched it since we were really doing this, but there were many horrible things that went wrong, of last-minute network configuration issues, et cetera, et cetera, et cetera. Perhaps the most memorable thing had to do with the weather. We were in central Illinois, and about an hour before our grand launch, there was a weather report that said that there was a tornado heading straight for us. So actually, you can see, if you look at the, let's see where it is here. Yeah, that's a wind speed trace for Champaign, Illinois, from May 15th, 2009, and there was the tornado. Well, fortunately, the tornado missed, although somewhat narrowly, and sure enough, at 9:33:50 p.m. Central Time on May 15th, 2009, I pressed the Go Live button, and Wolfram Alpha went live. Lots of people started using it. Some people even understood that it wasn't a search engine, it was actually computing things. The early bug reports then started flowing in. It was sort of interesting. It's a different kind of bug. Oh, that was the thing that it used to do at the very beginning when something failed. And one of the bug reports said, somebody said, "How did you know my name was Dave?" So anyway, there there were all kinds of bug reports that came in the first night, actually, with, here are a couple. That was, OK. Fastest bird. Ducks are not just food. This is all kinds of funny things. Well, so well, not only did people start using Wolfram Alpha, companies did too. So through Bill Gates, actually, Microsoft hooked up Wolfram Alpha to Bing. A little company called Siri hooked it up to its app. And a certain time later, Apple bought Siri, and through Steve Jobs, who was by then unfortunately very sick, Wolfram Alpha ended up powering the knowledge part of Siri. And if you scroll down to the bottom of all sorts of Siri outputs, you'll see a little Wolfram Alpha signature line and so on. So OK, we're kind of getting to modern times. The big thing now is Wolfram Language. Actually, it's not such a modern thing for us. Back in the early 1990s, I was kind of going to break off the language component of Mathematica. We were thinking of calling it the M language. We even had people working on it. An example, a now notable example, was Sergey Brin, who was an intern with us in 1993, working on the language, who sent me a nice piece of email that somewhere one can find that said, the real way to make money in the software business is by giving stuff away. But we'd never quite figured out how to distribute the language or what it should be called. Actually, back in the early days, Sergey's involvement with us caused, we swapped a Mathematica site license for with the early Google for a Google search appliance that I thought was actually still sitting in our server room, but I'm told that it seems to be gone now, and all that's left is its faceplate. So it goes. But the idea of making kind of a language out of taking the language that we built in Mathematica and making it sort of a language of its own, that idea kind of languished until we had Wolfram Alpha and the cloud existed and so on. And I must admit that I sort of was getting fed up with people thinking of Mathematica as being sort of a math thing. I mean, it had been growing dramatically over the years, and we kept on strengthening the math, but 90% of what the system was doing wasn't math at all, and the name Mathematica wasn't really serving it so well. And we had kind of a let's just implement everything kind of approach. And that had gone really well. We were really on a roll, inventing all sorts of meta-algorithms and automating everything. And combined with Wolfram Alpha, I realized that what we had was a new, very general kind of thing, a knowledge-based language that sort of built in as much knowledge about computation and the world as possible. And there was another thing, too, which was realizing that our symbolic programming paradigm could be used to represent not just computation, but also deployment, particularly in the cloud. So Mathematica has been very widely used in R&D and in education. I can tell you about lots of interesting uses that we know of Mathematica over the years, of inventing all kinds of things that one knows in the world. But with notable exceptions, like in the finance industry, it's not been so widely used for deployed production systems. And one of the ideas of the Wolfram language in our cloud is to change that and to really make knowledge-based programming something that can be deployed everywhere, from supercomputers to embedded devices. Well, there's a huge amount to say about this. If you happen to be really interested, I'm giving a talk at Stanford at 4 o'clock today, just about that topic. And we've done lots of other, what's this? That's the first 10,000 days of Mathematica. That's kind of a what kinds of different things were in it over the years. We've done all kinds of other things with our technology. I don't know why I have this picture here, but I have to show it anyway. This was a picture that on the commemorative T-shirt for an image identification project that we did a year ago using a sort of an AI project. And maybe you can figure out what the caption to this means with respect to debugging the image identifier. It was an anteater in the image identifier because we lost the aardvark who is pictured there. Anyway, but in just actually the last few weeks, we've done something which I'm excited about, which is that we have opened up our open cloud. It's kind of like what we did with Wolfram Alpha, of sort of trying to democratize access to computation by just having a cloud here that you can just go to and start computing with. It's really to let anyone use Wolfram Language on the web, sort of a culmination of 30, perhaps 40 years of work that I've done. And it's, you know, for the last 30 years, I've been working hard to sort of make sure that the Wolfram Language is well designed, that as it gets sort of bigger and bigger, all the pieces fit nicely together so that you can build on them as well as possible. And it's really nice to see how well this has paid off now. I mean, it's cool. We've got sort of a new kind of language, something that's useful actually for communicating not just about computation, but also about the world with computers and with humans. I mean, you can write tiny programs. There's this cute little thing called Tweeter program that is about writing programs. Those are all things made with 140-character programs. And you can also write big programs like Wolfram Alpha, which is written in Wolfram Language, which is 15 million lines of Wolfram Language code. So it's pretty nice to see companies in all sorts of industries starting to base their technology on Wolfram Language. Another thing I'm really excited about right now is that with the Wolfram Language, I think we finally have a great way to teach computational thinking to kids. I actually recently wrote a book about that you can find free on the web, but where is it? I think I had one here. Yes, there's an actual book. It's sort of an interesting thing, trying to figure out how to teach, you know nothing about programming, nothing about math. What is the trajectory through which you can teach computational thinking? And it's kind of, math has had 1,000 years to work out the sequence from arithmetic to algebra and so on. This is my attempt to do the same kind of thing for computational thinking. Well, after this whole journey, I sort of can't help wondering what would have happened if the 12-year-old me had gotten a copy of this book instead of that book about statistical physics that I showed, and if my first computer language had been Wolfram Language instead of the machine code of the Elliott 903. I certainly could have made some of my favorite science discoveries with one-liners, and a lot of questions about things like AI that I asked would already have been answered. But I'm pretty happy to have kind of lived at the time in history that I have, and to have sort of been able to be part of sort of these decades in the evolution of what I think is kind of the century and perhaps several centuries most important idea of computation, and to have personally had sort of the privilege of being able to discover and invent a few things relevant to it along the way. So that's really all I had to say. You can find, if you're interested in some of these things, there's a few websites that have related material. And thank you very much.
Some questions for you?
Yeah, great.
And we've only got about 10 minutes, so maybe just do 2 or 3 of them right away.
Okay, I'm happy to go on if people...
Okay, we'll go.
Yeah. Okay, so I have some questions. Okay, first question here is... I'm not used to index cards like this. They used to do this in Soviet Russia. I remember visiting there. They used to have index cards. Thanks. Okay. How does the integral algorithm work, and how does it recognize which integration techniques to use? Trig substitution, integration by parts, etc. It doesn't use any of those techniques, really. It uses a big industrial machine that does pretty much any integral in terms of an elaborate class of higher mathematical functions, typically things called Mayer-G functions, generalized hypergeometric functions, and so on. The big challenge is not to do the integral. The big challenge is to turn the answer into something that a human will recognize as a useful thing. And actually, one of the things that's sort of ironic, if you go to Wolfram Alpha and you type in an integral, you say integrate x squared sine squared x or something. It should compute the integral here. It takes it, milliseconds to compute that integral, and now it's showing us sort of a little report about other things it thinks we might find interesting. If you want to, you can press step-by-step solution, and this is a popular thing for students in the modern world. And this is That was actually a rather easy integral there. This is a complete fake. This is not how the underlying engine computes the integral. This is a lot of trouble that we went to. It's much easier if you know the answer to kind of synthesize steps that a human might have gone through to do the integral in a way that a human can understand. Next question. Why did you release Mathematica free for the Raspberry Pi? Because I thought it was a good idea. And because I thought it would be a nice environment. We wanted people to learn about programming and so on. It's a nice environment for people to sort of hook up lab experiments and so on to the Wolfram language. Actually, we have some very interesting embedded processor kinds of things coming in the future. Next question. How will Wolfram Alpha change in the future? Well, it's always learning about new things. I mean, it's getting a feed of data every second. Some data comes in every second, whether it's flight tracking data or whether it's, the earthquake feed. Some data comes in every year, whether it's some new Census Bureau data and so on. We're gradually adding more and more domains to the system. Over time, as we've taken things which we put into Wolfram Alpha and built them into Wolfram language, kind of the requirements of sort of computability and quality of data go even higher in the Wolfram language than they were in Wolfram Alpha. And in the Wolfram language, people are really making much deeper use of the things that we built in Wolfram Alpha. You'll see Wolfram Alpha able to do more and more kinds of things. There's the public version of Wolfram Alpha. There's also custom versions of Wolfram Alpha that we've built for all kinds of companies and other large organizations. Those do all sorts of interesting things. Actually, there's one very big installation, Wolfram Alpha installation, which will be coming out. It won't probably say it's a Wolfram Alpha installation, but it's a big consumer-facing retail type thing that's coming out in a few months that's based on a Wolfram Alpha. So those are some things that will happen. There are a bunch of new things coming in terms of just being able to understand more and more things that people say to their computers and phones and so on. What hard problem has Mathematica solved that had not been solved before? Wow. Well, I don't know, like if you look at the gravitational wave discovery that was made recently, Mathematica was used for the symbolic computations and then leading into all the numerics that was used to compute the orbits of those black holes. I happen to know that. It was also used for the movie Interstellar, which was the movie version of things like that. It's been used, gosh, I don't know. I mean, if you look at the kind of literature of the hard sciences, you'll find just tons of places where Mathematica has been used. I don't know, the proof of the Kepler conjecture, for example, that was sort of open for a few hundred years, that was done with Mathematica. Somebody told me, I mean, there are lots of inventions made with Mathematica. Somebody told me that the original codec for Skype was developed with Mathematica. The people I know, the Google AdSense algorithm, I believe, was developed in Mathematica. I mean, all kinds of things that over the years have been developed with Mathematica. But it's a consumer product. So we sell them, people use them. They don't necessarily tell us what they do with them. And actually, I usually find out a decade later when I run into somebody at an event like this, and they say, by the way, did you know that such and such a thing was done with Mathematica? Which is very neat, but there isn't really a systematic way to do it. Next question. How do you see the future of Wolfram Research's tools in life sciences research? Oh, there are all kinds of things going on in that area. Well, one nice thing, there's a company that's making use, a local company here that's making use of our tools in a nice way. There's a company called Emerald that has a lab in the cloud that is completely built with Wolfram language. It's cool to go visit them because even their machines are labeled with Wolfram language code. And that's but basically the idea is you write a Wolfram language script. You, in a private version of our cloud, you kind of press go, and then robots and some humans kind of swing into action and do your actual lab experiment, and then put the results back into the cloud for analysis. So that's an example. I think in general, I mean, we've been pretty active at supporting all kinds of genomics types of things. I think that in terms of modeling in biology, people have done, I don't know, there's what's it called, a systems biology markup language, which is closely connected to Wolfram Language, that's used by people, lots of different kinds of things. A bunch of the science that I've done has also gotten used a bunch in biology, often with simulations and so on done in Wolfram Language. Next question, what inadequacy in maxima led you to start SMP? Why not extend maxima? Good question. I talked to the people who developed maxima, and it was there was a bifurcation. The younger people said, it's the best they'll ever be. It's not possible to do anything better than this. The older people typically said, yeah, of course you can do better, but we're kind of too tired to kind of start building a new thing from scratch here. Mostly it was the language, which is kind of an algo-like language that was a pretty bad match for the kind of programming I wanted to do, things as mundane as kind of memory management and so on, and ran out of memory when I was trying to do the things I wanted to do, those sorts of things. I mean, it really was a pretty nice system that had been built. It was very specifically oriented towards doing algebraic computation. I, for example, built a big package for doing Feynman diagram computations, built some other stuff for doing things like tensor manipulation, which it wasn't particularly suitable for. It was something you could get it to do, but really the focus was, do sort of the AI project of trying to get a computer to do kind of freshman calculus course, at which it was very successful. We would like a graph of cancer versus golf courses in my town. Does the Wolfram language make this easier? Wow. I mean, I think that we have a certain amount of data, public health data and things like that. I doubt it goes down to the level of a specific town. That tends to be not data that we've often seen that data because there are things like custom versions of Wolfram Alpha that have been built for large healthcare systems where we've seen that data, but we can't make that available to people. I think the only other thing I would say there is that one of the things that we have this thing called Wolfram Data Drop, which is a way of basically dropping data from devices into our cloud, and that's a good way to have like IoT sensors and health-related sensors be able to send data to our cloud for analysis and for use by people. Okay, next question. Does a new kind of science impact the formalization of mathematics? Is math invented or discovered? Yeah, I've actually, my work in new kind of science has quite a lot to say about foundations of math. I mean, one example, I've spent a lot of time kind of exploring the universe of simple programs. Let me see if I can pull up an example here. Let's see if this works. Hold on. There we go. This might work if I'm lucky. So, I've spent a lot of time studying these things called cellular automata. This is kind of an all-time favorite example. It's called Rule 30, and it's just got that simple rule at the bottom there that determines the colors of black and white cells. And the question is kind of, well, you can ask what's remarkable is that such a simple rule leads to such complicated behavior. In sort of the universe of possible such rules, there's a large diversity of what kinds of behavior happens. Some of the behavior is very simple. Sometimes it's very complicated. Kind of, I think, sort of one of the big ideas of new kind of science was sort of the secret of nature has to do with how complexity gets made through just these simple programs running and producing sort of irreducibly complex behavior, and one can make that much more precise. And for example, one of the things that came out of that is finding sort of the simplest universal computers. Like there's a simple Turing machine. A few years ago, we ran a competition to find out whether the simplest Turing machine that I'd identified as a possible universal Turing machine is actually universal. And some young person in England won this, and so now we know this is the simplest Turing machine that's universal that could ever exist. So a thing that happens in mathematics, when we look at mathematics, There's a certain sort of set of axioms that people have used to set up mathematics. Just a single page is enough to basically give all the axioms that are used commonly in modern mathematics. And from these axioms, there are about 3 million theorems that have been published in the historical literature of mathematics that all flow from these axioms. And so sort of an obvious question is, why these axioms and not others? You know, if we just look at the space of all possible axioms, what's out there in that space? And you know, you can do things like you can say, okay, let's look at possible axiom systems down the left and possible theorems across the top and say, you know, when's a theorem true for a given axiom system? And basically, every row of this picture is like a field of mathematics. And so you can ask, well, where does the mathematics that we know and like, where does it lie in the space of all possible mathematics? And so one example where I was able to really nail that down is in the case of logic. There is sort of standard axioms for logic, and turns out you can represent, as everybody in Silicon Valley probably knows, you can represent all of logic in terms of NAND, because that's what, you know, microprocessors ultimately do, or NOR. And one thing I figured out is if you just search in the space of possible axiom systems, you don't have to go very far. It's about the 50,000th axiom system. It's just that one axiom, and that is the simplest axiom for Boolean algebra, for logic, that exists. So in this sea of all possible axiom systems, the one that we call logic is number 50,000, roughly. And that's sort of interesting, because it's like, what are all the other ones? Well, the other ones are other possible theories of mathematics, other possible ways that mathematics could have evolved. They're not. It's not the case that the ones that have actually been chosen are the ones that are uniquely relevant to our universe, because it seems like our universe is making use of all kinds of simple programs that correspond to other axiom systems. So in the end, my sort of meta-conclusion about the evolution of mathematics is that it's really something where, you know, in ancient Babylon, there was arithmetic, there was geometry. In the course of mathematics, there's been sort of a progressive generalization of those two fields, and that's led pretty much to mathematics as it exists today. I mean, this kind of philosophical discussion, it's interesting to do this philosophy. What I sometimes like best is this philosophical stuff has a real practical consequence for how we start building things that actually implement pure mathematics and so on. And I can talk about that if people are interested, but there's going to be, in the next few years, there's going to be some super interesting things that come out in being able to represent kind of all of pure mathematics in kind of the symbolic form that we're able to process in Wolfram language. Okay, last question here. Oh, wow, okay. This was about this related thing. Okay, please comment on the historical significance of the new Wolfram/Sloan Foundation/Fields program on semantic representation of mathematical knowledge. Wow, that's very specific. So this was this was just a few weeks ago. It's a thing I kind of started a while ago is like, how do we represent kind of the concepts of pure mathematics? People have, in the course of, I mentioned there are about 3 million published papers of mathematics, that 3 million papers, 3 million theorems, 100 million pages roughly. That's the complete corpus of mathematics. It's about 1 million person-years of work, including a lot of duplication, actually. And it makes the 5,000 or 10,000 years of work that have gone into Wolfram language seem not so insubstantial relative to that. But in any case, so the question is, how do you find, is there a way of finding sort of a symbolic language representation for those kinds of things? And a lot of what I've done in Wolfram language is finding symbolic language representations for things. So first of all, representing kind of concepts in computation, then things about the real world, whether they're cities or processes that go on in nature or in engineering or whatever, finding ways to represent those things symbolically. So there are several new frontiers of that kind of activity. One is in something like pure mathematics, representing all of the theorems of pure mathematics in a computable way. Another frontier is things like representing everyday discourse in a computable way. That's kind of an interesting thing, because it's a field that was much investigated in the 1600s of things like the philosophical languages of people like Leibniz and Wilkins and so on, but hasn't been much investigated in the intervening years, and that's kind of another direction for sort of making the world symbolic, so to speak. All right, I think we ran out of. I'm happy to go and answer more questions, and I even could answer questions about history. These were all questions about the future. I'm real happy to talk about the future.
Could we, could we wrap up the lecture and have you maybe speak individually after?
Yeah, sure. That's great.
Sorry. This concludes our program for today. Please join me in thanking Dr. Wolfram one more time.